What you're looking at right now in the Desmos online graphing calculator is a ball in 4 dimensions of space. Now this is not a shadow, this is not some projection or something. This is the actual ball itself as a sphere with completely solidly filled in. And the way I'm displaying it in 2 dimensions here on the screen is to take square slices of the 4-dimensional shape and display them side by side. So this is you're viewing cross sections here in 2 dimensions. So we're cutting it in 2 different directions. So the specific way that I've accomplished this is, well, if you want to look at the equations and stuff, it's right here. But in short, there are 2 dimensions on the screen, and 4. I have to somehow map that onto a 4-dimensional shape for the graphing calculator to test whether or not something is inside the shape. So, so on the x-axis here, we have both the x and the z-axes in 4 dimensions, and so you can see that the x is repeated over and over again. So it's taking the same view of the x-axis continuously, but on the z-axis we're just taking small steps up. And I can vary how far apart these steps are with this variable c right here. So as you can see, as I separate the slices on the z-axis, the shape seems to disappear because we're not cutting it as much, we're not cutting it as thin. But as I bring these slices closer together, the shape appears to re-emerge and then spread out as far as you can see. It's still the same size of shape. It's just we're seeing more of it because we're taking thinner slices. And this is just, I guess, an artifact of using Desmos for this, but you can see certain imprecise tiny details here are going to be flickering in and out of existence sometimes. I can't help that, I don't think. This is my first time trying anything more than just a simple graph on Desmos, so it may be a little bit wonky, but I also have this going on the y-axis as well, so y covers y and w, and it is the same variable that controls the density of the slices on both of them. I could separate this out, and for a couple of shapes that might be useful to do, but I guess I just didn't want to. It was a little bit complicated, I guess, to just do that for one thing when it would, for most other shapes, more square view is appropriate. So right now, I have this displaying the 4 ball, that is the set of all points that are equidistant from a single point in 4D space. But I've also programmed in a few other shapes here. And here are the equations. I've taken these from the Polytope wiki. So first of all, after the sphere, I have buttons here. So what these are going to do are they're going to swap around the different axes so that we can see the shapes from different angles. It's more of a reflection than a rotation, but with shapes with as much symmetry as these, it might as well be a rotation. So if I just click this, so these buttons are to just change that angle, and then reset is just to return it back to this order of 1, 2, 3, 4. So like if I switch x and y, z, w, this one sends x to z and y to w, and then reset just fixes everything. But since this is a sphere, nothing changes. Anyways, the next shape is the sphere of torus. And this one is defined as the set of points in 4D space that's the same distance away from a circle. So this is one view of it. This is another view of it. And most of these shapes, so this the ball only deals with this radius here. The other two most of the other shapes deal with R and P, but the torus, which we'll get to in a moment, also involves Q, but we're not there yet. A few different angles on the shape. And sometimes, so this is the equation. Wait, no, that's the tiger. This is it right here. If you were to swap J and K or G and H, it doesn't do anything. So if you're pressing these buttons and you don't see anything happening, then it's you're probably trying to swap between the two that that don't do anything. Like that and that. Always reset the view. And the next shape is the torus sphere. This shape is defined as the set of points that's equidistant from a 3D sphere. So that it's technically a 2-sphere, but it is a 3D shape. This is a sphere that we're familiar with, and just increasing the radius creates the torus sphere. Now, an interesting thing about this one and the sphere of torus that we just looked at, they can actually link together. And I can change the view here, and you can see a different perspective on that. So this link is an actual link. If you were to try to combine a sphere of torus with another sphere of torus, it doesn't actually work. You can pull them apart using the fourth dimension. But for these two shapes, they actually close around each other and prevent each other from separating. So you can see if you were to try to move the green one up, down, left, or right on, I guess, these, let's just call this the X and Y axes right here, it just bumps into the red shape. So you can't do that. And if you were to try to move them on the bigger axes, the Z and W axes, well, this prevents the green shape from moving this way in Z. This prevents it from moving that way. And in W, this right here prevents the red shape from moving this way. And this over here prevents the red shape from moving that way. So it's blocked off in every single dimension, with the only caveat being that it can actually rotate. There is some freedom to move around in a circle. Up next is the shape that I mentioned earlier, the torus, which involves R, Q, and P. Now, this shape is what you get if you start with a normal torus in 3D, and then you take the surface of that, and then all of the points that are equidistant from the surface of that 3D shape. So if you imagine stacking these slices on top of each other, you will get just a solid circular loop. And if I increase the radius, this is just the resulting shape. It gets a little bit tricky to follow in some of these angles. And I definitely haven't shown all of the interesting ones, but I will include a link to a snapshot of this Desmos file in the next one in the description of the video if anyone wants to play around with it for yourself, because there will be things in this file that I'm not showing off right now. I'm going to save it for a future video because scope creep has really gotten to me with this project. And the final shape here is what's called the tiger, which apparently is a pun based on the Japanese word for tiger, I think, and the torus. Anyways, this is defined as the set of points that is equidistant from another shape called the Clifford torus, which is what you see here. Clifford torus is the Cartesian product of two circles, for those who understand what that means. It can only exist in 4 dimensions. It is basically the same as a normal torus that you'd see in 3D, the surface, but there is no curvature to it. Like, even though it's curled around, if you were living on this shape in 2D, you would not be able to tell that there is any curvature at all. It would just look like a looping space, a looping rectangle of space. So technically, with this tiger, and I guess with the Clifford torus as well, you don't necessarily have to have the diameters of both of these circles, the bigger circle and the smaller circle, or they're not bigger and smaller, the XY circle and the ZW circle. You don't necessarily have to have them be the same radii. You can change it up a little bit, and then I just kind of call this the rectangular Clifford torus instead of a square one. But you can see either the small radius is on the XY plane here, or it's in the ZW plane here. But it is the same shape. And if I increase the radius again and change this back to a P, this is one of my favorite views. If I change this to 0.5, yeah, this view kind of surprised me when I was first thinking about how I would display this shape. When I was drawing this out on the notebook, thinking about how it would work, I thought about this kind of setup right here. I didn't expect that it would actually be real though until I graphed it out. But I just think this is really cool how this shows up in equations about circles. You get two loops right here that overlap and then negate each other in the middle. So yeah, there are only 2 views of the tiger from the cardinal directions. There's this one and this one. And this is the smallest circle, or the biggest circle that can fit inside of the tiger. And as I decrease the radius of the tiger, actually I'm gonna also decrease that. You can see how the Clifford torus starts to divide the sphere into 2 parts, the surface at least. So if you were to take the 3 sphere, which is the surface of the 4 ball, and on here that would be the collection of all the circles, not the full discs, but the circles on the outside here, then this would form a solid wall that would divide the sphere into 2 parts. You would have an inner part and an outer part, and they are both supposedly, I haven't seen it for myself, but they are identical. They are both solid toruses as we would know them in 3D. And you can see that because here so both of them have a ZW circle and an XY circle. And on the inside part right here, you can watch the ZW coordinate. You can take any ZW coordinate that's less than this radius, because we can get all the way to the middle of the shape here. And on the outside, we can take any XY coordinate, any radius in the XY direction, all the way to the edge here. Anyways, that is all that I had to show for this file in this video. I will come back to it later. I also want to show that I have made some of the less round shapes in 4D. So starting off here, there's the 5-cell, which is the equivalent of the triangle or tetrahedron. And yeah, I might as well go into a little bit more how I did this. So this greater than sign fills in the entire thing. This C1, C2, C3, and C4. It's just a fancy way of combining all of this stuff where we have the equations that I showed off from before and rearranging them and possibly even negating them. Like if I do minus y, you see flip turns to -1. So this is the 5-cell. And here you can, in this view, you can see that it's this is a tetrahedron right here, spread out into slices. And then there's another tetrahedron, and another, and another, and another, and it just gets smaller and smaller all the way up until a point. And here is another view of that. We've turned it inside out, so now everything looks like a downward pointing triangle, and the big shape is itself a tetrahedron. So that's the 5-cell. So actually, this way of viewing these shapes has its limitations, of course. We can't really fit 4D space into 3D, much less 2D. So some compromises have to be made. For example, if I were to increase the radius, you see that these shapes get cut off because I've divided all the space into squares. So we're only ever going to see this square of the XY plane. ZW plane is not limited. It goes on in all directions forever. But we don't see it continuously. We only see it in small steps. And additionally, the nature of having it be having these square samples of the 4D shape, or arranged in a square lattice, we only ever really get to see clearly the more symmetries that lend themselves well to the numbers 2 and 4. So like rotations and all that kind of stuff. But only in groups of 4 and reflections. But whenever it's like a triangle, when it's groups of 3, it's a lot more difficult to see. And I've considered what it might look like if I were to instead tile it by hexagons. I haven't really put in the time or effort to figure out how I would program that in, though. That might be a challenge for someone out there if anyone feels so inclined. Anyways, I'm going to turn this radius down, turn this back up. And again, I've taken these equations from the Polytope wiki. Now you might notice I've used the max function here, and these are more equations of planes than they are of points. So instead of programming in the individual vertices for these shapes, what I've done is I've started with all of space and then faceted off the sides of the shape. And in order to do that, I had to use the coordinates of the dual of each shape. So in this case, the dual of the 5-cell is just another 5-cell. So I could plug in the coordinates of a 5-cell and it would give me a different 5-cell. The next shape here is the hypercube. And this one, when you think about it for 2 seconds, it makes complete sense. It's just a bunch of squares. And the squares are drawn out this way, this way, this way. And the 16 corners are the corners of the corner squares. And for these, you might as well not even bother with any of these buttons because they correspond to symmetries of the shape. They won't change it at all. And I do have more views of this that I might go over later. Up next is the 16 cell, which is the dual of the cube. It is the cross polytope, the orthoplex, whatever you want to call it. It's constructed by starting at the origin, you walk out in all of the cardinal directions a set distance, you mark a point, and then you take the convex hull. And a couple of other views get pretty interesting here. I'll go over those later in another video perhaps. Up next is the 24 cell. And yeah, this one's really interesting for a number of reasons. If you've ever heard of it, you know why it's interesting. So I won't worry about that too much here. This is what it looks like. It's a lot of octagons and squares and tilted squares. But if I set this back down to 1.01, I do that for rounding errors so that things don't disappear in what I'm about to show you. So we have this one, and you can actually see the 24 cell honeycomb. These are all of the different ways that a 24 cell can attach to another 24 cell with matching faces. So you see this blue attaches to yellow through this octahedron right here, which is spread out along the vertical axis. Blue attaches to green through the octahedron that's spread out along the left side of all of these different cross sections. So you can imagine taking this point and this line and these points and more points, all of these points and lines, and they together make an octahedron, which is tallest in the middle here, and then it spreads out to the sides. And then this one's a little bit tricky to see, but blue matches with red over here with this line and this line and this point and this line, this line, this line, this line, and this point and that line, which also makes an octahedron. Like you can imagine this on top of that makes a square, and then this makes another square, and then this makes a point. So if you were to, so the points of this, the vertices of this 24 cell are these 4 corners, these 16 corners of the middle shape on the side, and then these 4 corners in the middle. And that makes 24. The faces are basically all the different things that you've seen these attached to. So we have the 4 that go along the outside. We have the 4 that represent the sides of each 2D slice. And then on each quadrant, we have ones that attach, like this blue and red one right here. So on each quadrant, you can pick bottom left, top right, bottom right. And together that makes 24. And now, you see, none of these things will change what the blue does, but the other 3 will be moved around. I had some fun playing around with this. So you can really see how all of these things stick together, and the only overlap you see here is just because I don't want certain things to disappear. So if I just send that back to where it was at the start, and I were to make this 1.0 instead, a lot of these shapes just disappear, and that's just a rounding error, I think. That's my best explanation for it. Anyways, moving on from the 24 cell. This one looks smaller, but that's just because it's a lot more complicated. So I increase the radius, and some of you might be able to recognize that these are cross sections of a dodecahedron, which means that this whole thing is a 120 cell. Now, I'm not going to go through and point out all of the different vertices. That would take forever, and I haven't mapped them out, and I don't think that would be worth it. But just know that it's all here. So this is how I have the golden ratio here, and then I have these operations that act on all of the even permutations of a certain coordinate, I guess, or plane, and all the odd permutations, and I just combine them with all for wherever that's useful. And then, yeah, here we go. This is the these are the faces of the 120 cell. Even permutations of these ones and all of these. Now the 120 cell, if I were to plot out their vertices, it would be a lot more complicated. These are actually the vertices of the 600 cell, which is the dual of the 120 cell. But it just ended up working out that the simplicity of those ones carried over to the 120 cell, and the 600 cell ended up being a whole lot more complicated, as you can see in this one, which these are all corresponding to the vertices of the 120 cell, but they're the faces of the 600 cell. Spoiler alert, that's what's coming next. 600 cell. Now you might also be able to recognize, if I can get a good view of it, actually no, increasing the radius isn't the way to go. I want to thin the slices a little bit. My computer's struggling a little bit. Those of you who are familiar with the slices of the dodecahedron might be able to recognize the slices of the icosahedron here. All lined up like this. This is the 600 cell. It doesn't have icosahedron faces. It does shrink to a point, but that point kind of expands into an icosahedron. It's made up of tetrahedra, actually, but they're all a little bit difficult to see. This is a really round shape and really complicated, and I can't hope to point out all of the features here. This is not the last shape that I've programmed in to this into this presentation here. I have a couple more that have been faceted from the 600 cell in certain places. In fact, I'm going to show you that right now. So here I have a 120 cell, which has been scaled up by a certain amount. And here is the 600 cell. Now this constant right here is the ratio of one of their in radiuses and one of their circumradiuses, radii. And the reason I've done that is to make it so that the vertices of the 600 cell are exactly touching the faces of the 120 cell. And so you could see one of these is perfectly fitting inside the other. And then if I were to add this shape, which fits inside the 600 cell, it's got some interesting symmetry. There's kind of a strip of green that's been cut out from the red in this direction and in this direction. And if I were to invert these, now it's on the axes here, but tilted in the other direction here. Now I wonder if anyone can identify what this shape actually is that I've created in red. It'll be an extra challenge before I reveal it in a future video. Yeah, so that's all for me for now. Definitely play around with this, and I really think that this has potential to help visualize different 4D shapes rather than trying to sort through a whole bunch of different projections and stuff and confusing rotations. And I think it's got some merit to it that even 3D cross sections don't have, because this is able to actually show some of the symmetries here that you wouldn't see otherwise.